Hi everyone! In the last video I talked about the hardware side of Medusa HC, and I promised that the next one would cover the software. And here it is. Today we'll figure out how all of this works in the inside. But before we get to the main topic, I want to answer a question I didn't answer in the previous video and share some updates. The question is, can Medusa HC be installed on printers other than Duender? Yes, it can, but some modifications may be needed. Actually, modifications will be needed either way. At the very least, you'll need to figure out how to mount the 2020 profile with the docks on your frame. One of the Discord users has already built Medusa HC on another Core XY printer, and from what I hear, it works fine. There were also questions about Vorons. I'm not sure, but it seems like someone is already working on it. If you have a Voron with the flying gantry, there are two options. You can do it like a stealth changer, where the whole system sits on top and the gantry moves up to it. Or you can make the dock station move together with the gantry. And if you have a Voron with the classic Core XY, then it's even simpler. You just need to make a front mount and that's it. But with off-the-shelf printers like Creality K1, GDQ2 and similar ones, unfortunately, things are much harder. And most likely installing Medusa HC on them will be either impossible or very difficult. There are two reasons. First, printers like this usually have very little free space inside, and without taking the enclosure apart and rebuilding the frame, you probably won't be able to attach the system without losing a significant part of the print area. And the second reason is the electronics. On off-the-shelf printers it's usually not very powerful, and it's sized just enough for what that specific printer does. Most likely you simply won't be able to properly connect extra hot ends, thermistor, fans and everything else, which means you'd have to replace all the electronics, and at that point it's essentially a completely different printer. Now for the news. To my own surprise, I decided to try installing the fifth hot end. And it turns out it fits just fine. Everything works, no issues. The only downside, there is no more room for the camera. And one more idea I want to share. I don't know yet when I'll get to it or whether I will at all, but I have a thought to try moving all the hot ends from the front to the back of the printer. Turn the axis around and move the whole dock system to the back. The idea is to keep the hot ends from sticking out in front, blocking the view, and to keep the tubes out of the camera's field of view and the operator's line of sight. There are some questions about maintenance access, of course, but we'll see how it turns out. Okay, let's go to the main topic of the video, the software side of Medusa HC. And as usual with me, it's some kind of weird tradition by now, I underestimated the volume of information again. And once again, I only realized halfway through that it wouldn't fit into one video. When you're talking about your own project, it feels like every little detail matters, and you want to explain why exactly this and why exactly here. So I decided to split the material into two parts. In this video we'll go over the main logic of the system, how it's built on the inside, how the printer understands its state, how tool changes work. And in the next video I'll show you step by step how to set up a system like this from scratch, using the example of building Medusa HC on my DoCR10 printer. The slicer setup, auto-calibration and preparation for the next print will also go there. It will make more sense this way. First understand how everything works, and then set it up with your own hands. This video will still be long and technical. Understanding how all of this works is genuinely important, not because I want to dump extra information on you, but because without understanding the internal logic, you won't be able to fully use the system, modify it and solve the problems when they come up. And they will come up, because this is DIY project, and I never promised it would be simple and easy, but I can guarantee it will be interesting. And since we are on the topic of DIY, let me remind you that all my projects are fully open source. And for them to keep developing and for the channel to keep growing, I really need your support. If you are able and willing to support me financially, the links to Patreon and Buy Me a Coffee are in the description under every video. Also, buying parts through my links helps a lot too. And of course, you're welcome to my Discord server. That's where all new ideas are discussed, prototypes get tested, and users' problems get solved. If you have questions while building or setting up Medusa HC, Discord is the right place to ask them. There is always someone there ready to help. From the very beginning, I wanted to try doing the software part myself. I already had some experience with tricky macros from when I was making my first multi-material printing system. So originally the whole software side of Medusa HC ran purely on macros. No scripts, no Python code, just Clipper macros and variables. And overall I managed to make a working Toolchanger. But when it came to more specific features and auto-calibration, it became clear that almost all projects related to multi-material printing systems are built on top of the base project for Toolchangers, Clipper Toolchanger. So right now, in addition to my own macros, something like a thin layer from Clipper Toolchanger is used for part of the tasks. And a separate Python script called pinwatch has also appeared since then. So things are a bit more interesting now, but all in order. Okay, let's start with how the printer itself is set up, because there are a few important points you need to keep in mind. Electronics. As I mentioned in the last video, my main board is a BIGTREETECH Manta M8P version 2.0, and the host is a CB2 that sits right on the board. In my case, it's set up so that the host talks to the MCU through a built-in CAN bridge. Since I recently added a fifth hot end, I needed another board. There were no free ports left on the Manta M8P for another extruder. So I just connected a second board, an SKR 1.4 Turbo, over USB, because I had one laying around. When the board is connected as a second MCU, its pins in the config are written with the MCU name. So instead of just PA0, for example, you write board name, then colon, then PA0. I'll probably come up with something simpler for the fifth hot end later, and in any case I was planning to move Medusa HC to my Big 2 CR10. There I'll be able to fit 6 or 7 hot ends. Moving on, homing. I use sensorless homing, so no separate end stops on the axis. I also have the TMC Auto-Tune plugin installed, but it's not required. It's basically a set of optimized settings for different motors, so they run with the better tuning. I didn't really notice any obvious improvements, so if you don't have this plugin, don't worry about it. Sensorless homing isn't the most accurate homing method, but strangely enough, I've never had issues with it. To make sure homing always happens safely and doesn't knock the hot ends off their bases, it's done in a non-standard way. First, y-axis is homed, and it goes all the way to the max, which is to the back. Then a small move away and x-axis is homed. After that, y and x are homed again a second time. Because of this, the final measurements always happen from the same point, and the results come out reasonably repeatable. In my sensorless CRG file, I have separate macros for homing each axis, and a macro that replaces the built-in G28. For homing the z-axis, I use a BIGTREETECH Eddy Duo. It can work simply over USB, that's the easiest way to connect it, but I didn't want to use USB port for it, so mine is connected over CAN. Eddy gives you two very useful things. First, the offset calibration by tapping the nozzle on the bed. For that, there is a project called EddyNG that enables this functionality. Second, the very fast and accurate bed mesh probing. For the probing to happen smoothly as a continuous scan without pauses on each point, you need to use the rapid parameter. I have a special macro that calls calibration in that mode. With Eddy, I couldn't find a way to take it work with the adaptive mesh. There might be a solution by now, but honestly, scanning the whole bed with Eddy is so fast that I don't really see the point. Worth mentioning here is line purge. It's a part of adaptive mesh. Personally, I only use the purge line itself, without the rest of the features. The stock line purge isn't very convenient because it sometimes gets in the way of the prime tower and the hot end movements on the first layers, so I modified it. Turned the line 90 degrees and now it's just printed in the front left corner of the bed, out of everyone's way. So now we get to the core, to how the printer actually understands what's going on. And the brain here is the pinwatch script. It's the one that constantly watches the state of the system. The whole logic of Medusa HC revolves around the data from the end stops. I have one end stop on the printhead on the carriage where the hot end is installed, and one end stop on each base where hot end parks. So in my setup with the 5 hot ends, That's 6 end stops total, 1 on the printhead and 5 on the bases. Knowing the state of all those end stops, you can always say exactly what's going on in the system. That's exactly what PinWatch does. It sits there constantly listening to the state of all the end stops, and based on that, it calculates which tool is currently active. It puts the result into a variable called current tool, which all the MedusaHC macros then read. The calculation logic is simple. The script looks at the head end stop and the sum of the base end stops. If there is nothing on the head and all the bases are occupied, the script assigns -1, meaning all the hot ends are in place and there is no active tool. If there is a hot end on the printhead and exactly one base is empty, the script assigns the number of the tool whose base is empty. That's the active tool. And if the data doesn't look normal, for example, there is the hot end on the printhead but two bases are empty, or printhead is empty but one of the bases is empty too, the script assigns -2, meaning an error or something goes wrong. The script itself doesn't decide anything and doesn't stop the printer, it just sets the value. What to do with that value is the macro's job, and we'll get to that. What I like most about this approach, all of it happens literally in real time. The printer knows at any moment what is where. You can even take the hot end off by hand, mess with it, put it back, and the printer will immediately update its state on its own, without any comment from me. No need to call any refresh macros, nothing. Now about the script's settings. They all live in the mhcconfig file, in the PinWatch section. There aren't many. There is Sync Toolchanger, that's synchronization with the Clipper Toolchanger plugin. I'll explain in detail what it's for in the next video, in the setup and auto-calibration part. For now, just remember that this option exists. Verbose parameter, if you set it to 1, the script will start printing detailed information messages about what is going on and how the state is changing. By default it's off, because in normal operation those messages aren't needed and just clutter the console. But if something's going wrong and you want to investigate, you can turn it on. And then end stop pins. The printhead pin is written as pin E, and the base pins as pin T0, pin T1, and so on. The number of these pins is used by the script to calculate how many tools are installed in the system. Since we're using plain end stops, the pin should be pulled up for the stable signal. In Clipper, this is done with the caret symbol in the front of the pin name. It enables the pull-up resistor inside the microcontroller. The exclamation mark next to it is signal inversion. Whether you need it or not depends on how your end stop is wired. If the state reads inverted, just add or remove the exclamation mark. And the last addition I made to the script is the indication in the web interface. Recently it turned out you can control the tool icons and color indicators in Mainsail, so I added this capability to the script. It controls by two settings: Sync Mainsail Tools and Sync Mainsail Sensors. They're independent, each can be turned and off separately, and they handle two different things. The first is the active tool indication. When a tool becomes active, its button in the interface gets highlighted. The second is the color indicator, and I set it up so it shows the actual state of the base end stops. If a base end stop is released, the indicator is red, meaning there is no hot end on the base. If the end stop is pressed, the indicator is green, the hot end is in place. We don't have place for a separate indicator for the printhead end stop, but we can still tell when it triggers. If the indicator of the active hot end turns blue, it means the installation was successful. The head end stop is pressed, and at the same time one of the bases is empty. So a blue indicator is essentially confirmation that the hot end is really picked up and sitting on the printhead. Moving on, besides the script setting, the mhcconfig file, as the name suggests, contain the base settings for the MedusaHC related parts of the system. Right after PinWatch there is the duplicate pin override block. Here is the deal. All the tools share a single feeder motor, but at the same time every extruder in Clipper is required to have its motor pins listed in its settings. so the same motor pins end up declared on several extruders. By default, Clipper complains about that and won't start. To stop it from complaining about duplicate pins, in the duplicate pin override block, you need to list the step, dir, and enable pins of the extruder motor. After that, Clipper allows them to be reused. Then come the settings blocks for each of the hot ends. Everything's standard there, just like for a regular extruder. The motor pins are the same on all extruders. Everything else, thermistor, heater, PID, is individual for each one. The unusual thing in these blocks, there are two lines, max extrude cross-section set to a bunch of 9s and max extrude only distance set to 700. Basically, they remove the extrusion limits. I added these parameters so line purge would not throw an error. Maybe there is a cleaner way to solve this, but this works, so I don't really worry about it. After the blocks for all the extruders comes a very important thing, the T macros. You absolutely have to create them. Simply put, these T macros are what make Clipper and Mainsail understand that the printer has several tools. These macros also create the tool buttons in the web interface. The T macros themselves are very simple. Each one has a couple of variables. Those are the indication variables I mentioned. One handles the highlighting of the active tool, the other the color of the end-stop light. Then there is a respond message command, that's just a text notification to the console. And the most important part, a call to the set macro with the number of the corresponding tool. So when you press, say, the T4 button in the interface, what actually happens is a call to the set macro with the parameter 4. This macro can be called the heart of the system, and we'll get to it soon. Next in the file are the fans for the radiators of each of the hot ends. They are connected to controlled ports and turned on automatically when the temperature of the corresponding extruder goes above 50 degrees. And at the very end of the file are the verify heater blocks for each extruder. These parameters slightly relax the requirements for heating speed and stability for the hot ends. At some point, when some of my hot ends were in a poor shape, I had some minor heating issues, and these parameters helped. But if your hot ends are in good condition, the thermal paste is new, and the cooling fan is of decent quality, there is no need to change these settings. The next important configuration file is MHC variables, and these are what you'll need to adjust for your own build first. I'll go over them briefly without too much detail. There is more information in the README on GitHub. The variables are split into several groups. The first group is Toolchanger macro. This is where all the geometry of the system lives. First comes the X coordinates for each base, the position where each hot end physically sits. Then there is Y safe, the Y coordinate at which the carriage with the hot end installed can freely move left and right without hitting other hot ends on the bases. Mine is negative because I used slightly extended Y profiles, so I wouldn't lose print area. Next is Y latch, the Y coordinate at which the hot end fully latches onto the base. It needs to be set very precisely, so the hot end pushes against the base firmly but without skipping steps. The X shift, the distance you need to shift the hot end along X axis to pull it out of the base slot. Also in Toolchanger you set the speeds and accelerations for the tool change. Then goes the coordinates for priming and cleaning. Y prime, the coordinate where it's safe to extrude filament into the bucket. Y brush, roughly the center of the nozzle wipe brush. And X prime shift, the distance from the base to the prime point. Toolchanger also has the feeder control variables I added recently, E open and E close. This is the distance and direction the extruder motor turns to open and close the feeder. The sign sets the direction. And there is E car high mult, a multiplier on the extruder motor current for opening the feeder. The boosted current is needed so the motor has enough torque to open the feeder against its spring tension, without skipping steps. Typically, it's somewhere between 1.3 and 1.6. The second group is global state. The main variable here is max tool. That's the number of hot ends in your build. You set it manually, and all the macros of the system rely on it. Apart from that, global state mostly contains service variables that you shouldn't touch. These are various current states, for example, the calculated motor current values, the target tool, the feeder state, error flags, and so on. Usually you don't have to touch this. The third group is the tool state macros, one for each tool. So tool state 0, tool state 1, and so on. I also added this recently to optimize priming with the different materials and different nozzles. Here the prime and clean parameters are set individually for each hot end. For each tool you can configure how much filament to extrude during priming, at what speed, what retract to do afterwards, then the nozzle wipe parameters, whether to enable the wipe motion, how far and where to move along X and Y, at what speed, and the retract after wiping. And separately the parameters for the very first prime of the hot end during a print, because the first time you usually need to extrude a bit more filament. And the last group is tool offset. Here are stored the offsets of each tool along the X, Y, and Z axis, relative to tool 0. You usually don't need to enter this by hand, because they are calculated automatically during calibration and loaded from the saved vars file. But we'll talk about auto-calibration in detail in the next video. Now let's go to the MHC macros file, and we'll start with the initialization, with the init sensor state macro. It's a delayed G-code that automatically runs a couple of seconds after clipper starts, and it gets the system ready to work. It does three things. It reads the feeder motor current from the TMC driver settings and calculates the boosted current value for opening the feeder. Then it closes the feeder with the close command, so the system knows its state from the very start. And it loads the saved tool offsets from the saved vars file to the tool offset variables. Basically, it's just preparation before work. Here I need to explain one important detail on how clipper macros works. Otherwise, it will not be clear later why everything is built this way. When a macro starts, Clipper takes something like a snapshot of the system state at that moment. This includes global variables and the states of objects. If those values change while the macro is running, the macro will not see the updates. It will keep working with the data it had at the start. Only the macro's own local variables can change normally while it's running. To get fresh data, you need to finish the current macro and launch the next one. It will take the new snapshot and see the updated values. That's exactly why many macros in MedusaHC are split into several separate ones that call each other in a chain. It's the only way I've found to make a macro see that the state of the sensor has changed after the printer physically did something. Now let's move to the feeder control macros, open and close. The feeder doesn't have a state sensor, so physically the printer doesn't know whether it's open or closed. And calling open again while the feeder is already open can jam the mechanism. So the state is stored in a variable called feeder open. Before opening, open macro checks it, and if the feeder is already open, it does nothing. Closing is safe, so close doesn't have such a check. And that's exactly why at startup the printer forcibly calls close to set the state of the feeder from the very beginning. How opening works. First, the servo turns with a short pause to let it finish moving. Then we raise the extruder motor current, the same boosted current that's calculated at startup, so the motor can overcome the spring tension without trouble. After that, the motor wiggles back and forth a little. This is so the gear of the opening mechanism meshes with the teeth on the motor gear. And only then, by turning the motor, the feeder opens. One important point: during opening, the feeder makes a small backward motion with the drive gears, and while the feeder hasn't opened yet and the grip on the filament hasn't been released, the filament makes a small retract. During a print, this isn't a problem. In fact, it's even helpful. But if there is cold filament in the hot end, the gears can chew it up a bit during opening. So try not to swap hot ends with cold filament inside. And one more bug I haven't found a solution for yet. If the motors were disabled by a command or just by the printer's timeout, then the very first feeder motor move command doesn't execute. So if the motors were sitting disabled, the server will press the mechanism, but the motor won't open the feeder. Simply enabling the motor doesn't help. To avoid this problem, some macros call close at the beginning, just to wake up the motor. But if you're swapping hot ends manually outside of the print, you'll have to take care of this yourself. Just give the motor one wiggle before the change. And finally, the heart of the whole system, the set macro. It's responsible for tool changes, and it's the one called by the T0, T1 and so on macros. Inside set, there isn't one solid block of code, but a whole chain of macros that call each other. And this is exactly where what I talked about earlier comes into play, the state snapshot. After each physical action, control is passed to the next macro, so it sees the updated sensor data. So set isn't one macro but several, and now I'll explain the logic without diving into every single movement. When you call some tool, the first thing the system does is look at what's currently on the print head. Then there are few options. If the head is empty, it's simple. The printer goes and picks up the requested hotend from its base. If the requested hotend is already on the head, there is nothing to do at all. The system just applies its offsets and finishes. But if there is a different tool on the head, then before picking up the requested one, the head needs to be freed first. In that case, the system first puts the current hotend back on its base and only then goes for the one you requested. And what's important, I never need to tell the system which hotend is currently on the head or where to put it. It figures all that out from the end-stop data. It knows what's installed, it understands which base it belongs to, and it goes to the right tool by itself. All I need to do is say which tool I want. And this is where it was talking about the checks, because they are what makes the system reliable. The state is checked at 3 points. The first time before any movement begins to understand what's currently on the head. The second time after the current hotend has been returned to its base to make sure the head is actually free. And the third time after the new hotend has been installed to make sure exactly the right tool is in place and that it sits correctly. If during any of these checks the state is wrong, the current tool is set to -2, the system enters error mode. I'll explain error handling separately. And there is one moment here that I don't really like myself. Between the checks there are small pauses, roughly a second each, so the sensors have time to update their state, and the check reads the actual data. In total it's just a couple of seconds, but it does stretch out the tool change a bit. I haven't found the way to get rid of these pauses while keeping all the checks, and the checks cannot be removed. It's possible that moving all the processing and movements into script would get rid of these delays, but I'm not ready for such a global rework yet. As I like to say, if something works well, don't touch it. One more thing worth mentioning, the macro chain also has many checks that look at whether the printer is printing or idle. In the idle mode, the system behaves a bit differently. During a print, when changing a tool, the head moves slightly away from the base, does priming and wipes the nozzle on the brush. In idle, none of that happens. The hotend just gets swapped without priming and wiping. And if an error happens in idle, the system just reports it and does nothing more. During a print, on error, the print gets paused, and we'll get to that. So in the end, the set macro is the entry point. When we call it, we pass the T parameter with the number of the hotend we want. From there, depending on the current state, one or another chain of macros runs, and they pass the parameter to each other like a relay. The same number is also assigned to the target tool variable. That will come in handy a bit later. A lot of different movements happened during all this, and tuning all of them was honestly a real pain. I optimized everything as much as I could and tried to make it so the printer cannot damage itself in unusual situations. Most of these movements are tied to the variables we talked about earlier. This is done so the system can be easily adjusted for your own build. There are still a few more values that I should expose as variables, and I will improve it gradually. But there is a limit you need to understand. For small differences in the build, changing variables is enough, but for serious changes, for example if you decide to mount the hotends vertically instead of horizontally, variables alone will not be enough. You will need to go into the macros themselves and adapt the movements to the new mechanics. In fact, these macros are quite simple, no tricky functions, no magic. Even if you are not very experienced with the Clipper macros, you should still be able to understand how they work. By the way, to make the logic easier to follow and also for initial setup, you can greatly lower the speeds in the variables. When the printer moves slowly, all of its movements becomes clear and easy to understand. Now let's talk about error handling, pause and resume. Let's start with the error state. The system has a separate variable that stores this state, and there is an error macro. When something goes wrong somewhere in the macro chain, the printer does not call pause directly, it calls this error macro instead. And from there, the behavior depends on the situation. If no print is running, error basically works as an exit for the macro chain. It stops further actions and that's it. But if a print is running, a modified pause macro is called. It moves the print head back to a safe distance and then calls Clipper's built-in pause mechanism, which saves the current coordinates so the print can be restored later. This gives you a chance to fix the problem by hand. For example, put the fallen hotend back in place or push in the hotend that didn't fully sit. After that, you can press resume. And resume turned out to be unusual. First, it homes X and Y. This is required because when picking up or dropping a hotend fails, the motors often skip steps. The coordinates must be reset. Then the target tool variable comes into play. As I said earlier, it stores the tool that the printer was trying to install before the error happened. So after homing, no matter at which stage the failure happened, the printer will figure out by itself which tool needs to be installed. The same set logic as during a normal tool change. And at the end, Clipper's built-in resume runs. It restores the saved coordinates and continues the print. There is one annoying part. The saved point, as you remember, is in the far left corner. So the nozzle will first go there to the saved point and only then move back to the model. By default, this move is very slow. To change its speed, you need to add a recovery speed setting to your config. And to close this part, let's look at a few useful macros that stayed behind the scenes. The first one is drop tool. It is used to simply return the currently installed tool back to its base without picking up a new one. Just drop whatever is on the head and that's it. The second one is clean. It wipes the nozzle on the brush near the base. Mostly this is needed for ADNG tab to work, so the nozzle is clean before touching the bed, but you can also call it manually if you want. And the convenient thing is that both drop tool and clean figure out by themselves what exactly to drop and where exactly to wipe. You don't need to pass any parameters. Next is home request. This is just an automatic homing request. If the axes are not homed, it homes them. If they are already homed, it does nothing. It exists so the same check doesn't need to be repeated in many different macros. They all just call home request and it decides by itself whether homing is needed. And the last one is test tools. This macro was actually made by one of my subscribers, a guy named Topi. It is the macro for checking that the system works. It simply picks up all hotends registered in the system one by one with the small pauses between them, and at the end it drops the last one. It is really a useful macro for quickly checking that all hotends pick up and dock correctly. Everything else that remains is related to setup, and that will be the topic of the next video. There I will not only talk about auto-calibration but also about slicer setup, because multi-tool printing has quite a few specific details there too. So there is plenty of material for the next part. And that's it for the main logic. Yes, the system is not perfect in some places. There is the room for improvement, and I'm slowly working on it. But it works reliably enough, assuming of course that everything is built properly and carefully. And once again, my projects are fully open source. All file configs and scripts are on the GitHub. The links is in the description. There you will also find links to Discord, where you can ask questions and chat, and ways to support the channel. Any support really helps. Like, comment, subscribe, and that's all for today. See you soon!